All right. Well, hello, everyone. Welcome to our first ESIP IT&I meeting of the new year. This is the Information Technology and Interoperability Committee. My name is Chris Battisto. I'm the current chair of the IT&I Committee. I work for the NASA Goddard Earth Science Data Center, and I'm excited to be joined by Dr. Narayanarao Bhogapurapu today for the first talk of our webinar series. The format of this webinar today will be 30 to 45 minutes for the presentation, with remaining time for any Q&A. And the recording of the webinar will be posted to the ESIP YouTube. Dr. Narayanarao is an assistant professor in civil engineering at the National Institute of Technology in Warangal, India. He earned his PhD in geoinformatics and natural resources engineering from IIT Bombay, where his award-winning doctoral work advanced soil moisture estimation using PolSAR data. Dr. Narayanarao has received multiple honors for his contributions to open source SAR processing data tools. And without further ado, I will pass it over to Narayanarao for the presentation on PolSARtools. Thanks for joining us today.
Yeah. Okay. Yeah. Thanks, Chris. Thanks for the introduction and the invite. So I think good morning, everyone, back in US, and yeah, it is actually evening here in India. So it's like 7:30 in the evening. So yeah, I'm Narayanarao Bhogapurapu. So today I'll be talking about our kind of my first-hand experience of developing an open source processing tools, specifically for the radar data processing. So the title of today's talk would be like the PolSARtools accelerating open science in radar remote sensing with cloud native processing. So let me share my screen. Is my screen visible?
It is. It looks great.
Oh, yeah. Thank you. So though I'm the lead developer for this, leading the work, so there's contribution from our peers and professors and supervision from it's a multi-institute collaboration, both from India and as well as in US. So without further ado, let's start and jump into that. So just before going into the radar data processing, let's just see kind of how radar works. A quick say yes. So here a quick graphic of the current NASA-ISRO synthetic aperture radar mission. So radar usually deals with the microwave spectrum of the electromagnetic spectrum. So it's the same energy of the waves which we use for the warming up our food in microwave ovens. So in short, what it does is it sends a short burst of microwave energy towards the Earth and just collects the returned energy or return pulses. So here what you're seeing is the current NASA-ISRO synthetic aperture radar mission in action. So which is actually the bottom part here is the Earth, and which is using a reflective antenna, which is like dual frequency, and these are like more technical words, but you can actually understand this as a different bands in terms of optical, if you're familiar with optical remote sensing. So in essence, it's an active remote sensing technique, and the data is mostly towards a signal processing rather than an image processing one. So that is a kind of a difference between a radar data processing versus an optical data processing. So can anyone guess this image? It looks familiar. So which place on the globe it is? Any guesses? I'm sure you might be familiar with this kind of good-looking pictures, which are mostly from optical remote sensing. So if you have collected the same image with a radar, so this is how it looks like. So mostly a grayscale. So each pixel is represented by the return energy from that area. So this is actually from Manhattan in New York. So, so now with that, we know how a radar data looks after processing. So let's see how many current satellites and the scale of the data sets. So currently the modern synthetic aperture radar missions are delivering petabyte-scale data sets annually. So the recent one is the NASA-ISRO synthetic aperture radar mission, which is kind of collecting roughly a 4 terabyte of data daily. And then we have Sentinel-1 constellation, which is a constellation of 3 or 4 satellites, 1 gone, but 3 are currently working, which is a C-band. And again, they're collecting terabytes of data annually. petabytes of data annually and terabytes daily. And there is a recent BIOMASS mission from ESA, European Space Agency, which is the first ever P-band SAR mission in the space. And the data is still not yet open because it's just a few months ago. Similarly, like NASA and BIOMASS have launched in like 4 or 5 months ago, like July, almost a year. But the data is still they are processing, given the complexity involved in processing the radar data in order before releasing it to the public. And the next two missions are mostly local missions. These are not global coverage. One is from ISRO, which is EOS-04, and another one is LO series from Japanese space agencies. And these are kind of currently operational and publicly available datasets from publicly funded space agencies. And there are satellites from Argentinian space agency that is called SOCOM constellation, and there are a huge category of commercial satellites as well, like Capella, Umbra, and so on. So there is a huge inflow of the data. Synthetic aperture radar data is available, but we are kind of on the other hand, we need kind of a tools or process or handle or make sense of the data. So we are actually way kind of behind or under utilizing these data sets in the sense that the earth science are data sets. So let's take a look at the open data policies. So it is kind of very recent, at least for the Indian landscape, that recently, like 2023, India proposed the Indian space policy. So where the entire petabytes archive of the entire ISRO has been made open to the public, which includes both radar data images as well as the normal optical images. And in 2023, NASA also took an initiative under the umbrella of the TOPS transformation to the open science, with a kind of a focused funding as in a kind of an experiment. And so this is kind of a scale of the open data and efforts from different space agencies, because European Space Agency also has been putting a lot of efforts to make the data archive openly available so that everyone can do open science. Now, take a look at the cloud era, because earlier these data sets used to sit in their local servers. A classic example would be the Landsat archive, which used to be handled by USGS, US Geological Survey. So recently, that's like 10 years ago, which is, I would say, kind of compared to the earth sciences, it is very recent. So there is a kind of a kickstart of migration of these data archives into the cloud, right? Let's say there is a collaborative or the effort between the NASA and Amazon Web Services in 2015. So then that's the first time they started moving the entire Landsat archive, the 30 years, 40 years of data into the S3 buckets. And recently and later into the SAR specific one. Currently, most of the SAR data from US side has been handled by the Alaska Satellite Facility. And in 2017, they're also migrating towards the cloud, like Amazon S3 buckets. And for the matter of fact, all the NISAR data, which is NASA-ISRO Synthetic Aperture Radar mission, will be hosted in AWS cloud. So now the data, the size of the data, and now the cloud, and now we need the tools to actually handle the size and the environment of the data, so the form of the data. So there are, sorry, I think there is some mismatch in the formatting. So there are kind of openly available tools, though there are a few more popularly used, let's say the ICE framework from NASA JPL, which is more specifically for the interferometric processing, and there is a SNAP toolbar from European Space Agency, and there is a PolSAR Pro Bio combined with the University of Rennes and European Space Agency. This is one of those widely used SAR processing software for polarimetric aspects, and there is also MIDAS, microwave image data analysis tool, which is from ISRO. And not all of them kind of developed in a kind of cloud native environment, because they are like started like 20 years ago. The PolSAR Pro has been there for like 22 years, and recently they decommissioned any updates. So that's the last version or the ultimate version they released. So, and they have written in C++. The core idea is to kind of reach to increase the community usage of the polarimetric SAR data, not as a large scale processing as currently we are seeing the inflow. And there is a platform called Multi-Mission Algorithm and Analysis Platform, which is again a joint initiative from NASA and European Space Agency. So this is not a toolbox as such, but this is a cloud native platform where developers contribute their algorithms along with the science team algorithms from the satellite team itself, so that it is kind of one place to host those algorithms, data, and end-to-end pipeline. But again, these are all mission specific, and there is a lot of disconnect. So if I talk about the Snap was written back in Java, and it has, though it is a very powerful and diversity tool, but in terms of polarimetric functionalities, it is limited. And there is a Python wrapper if you want to use it in cloud, but even personally, I couldn't actually configure it, use a Python version of it. ICE is a great tool, but there is no polarimetric options there. It's mostly focused on interferometric tools. So this is the current landscape of the data, the open data, or the size of the data and availability of the tools. So now we can actually see a huge opportunity here, the cloud era of it. So people require cloud native workflows and open source tools, because there are commercial tools as well. I haven't talked about that because this is mostly focused on open source, and because commercial tools are mostly way expensive, and a way that I can kind of give an example. Like there is one specific SAR processing tool called Gamma, which is so expensive. I'm not sure whether even 1 or 2 licenses in any academy of India can afford. So because I haven't seen any of top-notch Indian institutes, because kind of it's expensive, and also the community is very narrow to even invest that much money. So it is kind of in a way that since the data is open and we are moving towards the open science, so there is this kind of requirement of open source tools, because a closed group of a company can do only a limited task compared to the global scientific experts and the size of the community who can contribute. And there are again 2 ways of it in terms of open source tools. One is the tools which are like narrowed and niche towards that only the domain experts can use and with their coding skills. And there is another section of it anyone can use, a non-domain skills or non-domain experts or users with a limited coding and a GUI-based tools. So this is kind of an opportunity from the current landscape. So using that, we have actually formulated a list of objectives to actually create the PolSARtools framework. So the first one is that it should have an end-to-end framework. So as the data in its native format distributed by any space agency, so any user can download it or directly process in the cloud within any EC2 instance. Either it is a cloud native environment or a desktop environment, it should support both. That's the first kind of objective we have decided. So, and the other one is it should be also have an alternative non-domain users like a GUI interface or notebooks, or let's say a popular GIS platform integration. And the other one is, as I mentioned, in map and other initiatives are sensor specific or mission specific once the mission life is gone. So, or all the algorithms for the data products are again channelized for the mission. So we were kind of envisioned some kind of sensor independent, again inspired from the legacy softwares, that bringing all the sensors data into some common polarimetric format, so that from there anyone can analyze the data and also carry forward. And another important aspect we are looking into is not just the science or the core findings, but educating people or increasing the community and teaching. And this is equally important for the preparation of the next generation. So we have also included such kind of functionalities to show the simulated plots or some kind of plots and simulations, so that it's also useful for education, and it should be lightweight because for the educational institutes, and we need the quick results even for the small data and simulations and so on. And again, there is always requirement of a future scope, so that it should be also ready for the next generation or editions. So currently most of those cloud native algorithms rely on Python, so we chose the Python language for this, and plus for the speed on the back end, where this is high computational tasks are there, we chose C++ at the back end, but entire thing is again compiled into the Python code. So coming to the brief timeline of how this idea actually started. Actually, it started with as I started my PhD. So I have a habit of kind of writing codes to learn anything. So I used to get any radar remote sensing textbook, and I used to read and see all those plots and images, and I used to write and replicate those codes. So when I was actually compiling, this is how I'm learning. So after a year or so, I have like a bunch of codes. Then my professor actually advised me, so why can't you compile all these codes, since you have put a lot of effort, and just distribute it to, or share it to other people so that they can also use. They don't have to kind of spend the same amount of time. They can actually start where you left off, or they can improve it. So that is how we thought, kind of distributing this few sets of code. And again, at that time, so what we thought is the popular QGIS platform, where then we formulated a GUI interface to collect all the functions, and just with a few button clicks, anyone can kind of generate those derived parameters from polarimetric SAR data. So that's how it actually started. So once everything is ready, we also kind of went for a paper submission within a scientific peer-reviewed journals, Journal of Open Source Software, so that it gives a confidence and a validation that not just it is kind of a piece of code or a hobby or something, it is also scientifically valid, and so that people use it with confidence. So this is kind of an indirect way of giving that reliability, or kind of a trust that people can use it for scientific work. And then once we are kind of started with the GUI, so usually people start with the coding and the GUI, but we started with the GUI, and then we saw the scale of the data. So with the GUI, we are unable to kind of scale or automate and process a huge chunks of data into a kind of a native cloud environment, because we have seen that people are moving to the cloud and data is only available in the cloud. So then thought of making a Python package. So then again, we return and compile all the code into the Python package, and first Python version we have released in 2022. And then again, after a huge effort, like after 3 years, since we are confident enough that, okay, this is now in a kind of shape and form that ready for the scientific and large scale applications, then we actually compiled a paper and submitted. Recently it got accepted in Elsevier Software X. And then very recently, we have kind of released our recent version of PolSARtools, which supports the currently available spaceborne, airborne, and also one planetary sensor, which is Chandrayaan-2, which is a radar orbiting the moon from sent by ISRO. So currently, those are the available functionalities in the recent version of PolSARtools. So let's see the architecture and the functionality of it in a way. As I mentioned in the our core objectives, it should be kind of cloud compatible, cross-platform, and also it should be platform independent. That is one of the objectives. So that, let's say, I can my personal experience from working in US versus India. In US, I can see a majority of those computations or the people uses either Mac or Linux. But in India, if you see the user base or the community is completely different. Most of them, mostly more than 80%, uses Windows here, and very less fraction of that Linux and Mac users. So if I can give you an example of the previous softwares, let's say an ICE example, which is developed by JPL and only available for Linux and Mac. So most of the Indian people, they had to set up a Linux environment and has to do a setup. I've seen the students here struggling even setting up the software itself, just getting it to run, and a long way to even process the data. So though currently, so our target, what we targeted is it should be kind of independent of it. It should be Linux, Windows, and Mac. So, and also we have kind of organized those modules because we have different forms of polarimetries like full, compact, dual, and others. And also for visualization and analysis and education purpose. So, and also we have structured in a way that for the future, if you want to add any new sensors, so you can directly modularly add at the sensors level so that the entire pipeline stays the same. So it is a brief architecture or the kind of categorization of the modules we call. So the processing, the first one actually deals with the sensor independent data. Let's say we have a different types of sensors, sensor data. Let's say some people distribute, some agencies distribute with the raw binaries, and let's say some agencies distribute in GeoTIFFs, and now recently the NASA introduced HDF5 file formats, like hierarchical data file format. So these are like different formats agencies are distributing it. So in order to compile or get, so input your any sensor data and get a common format, mostly a cloud native geotiff, or we call COGs, so cloud optimized geotiffs. So that is what the first step of processing will is kind of framed to do. And the analysis part mostly do the second order things. Mostly the analysis, the descriptor, different decompositions, different vegetation descriptors, and so on. And the visualization part is mostly the simulation plots, all publication ready. So these are like third level processing. And coming to the PolSARtools QGIS plugin, as of now, except the sensors module, all other modules are actually integrated into that. So with a few clicks, you can directly process the polarimetric data and derive all those descriptors. So in my opinion, the documentation and tutorials carries an equal weight as the software itself, because even though, let's say, we have written a well-structured, super nice code and very sophisticated processing, but no one understands how to use it, or then it is of kind of as good as of not available. So that's why we actually put an equal amount of time. This is one of the challenging tasks for us, to create a proper structured documentation for and all the functions, because we have more than 100 functions currently, so 100 unique functions. So here is the code example, a small snippet along with the comments to actually process the NISR data. So you can actually see an end-to-end. So you can import the data and extract a polarimetric matrices and do a decomposition and visualize it as a plot. So the output will be something like this. Oh, so something happened with the images. Sorry for that. But yes, so this is kind of a simulated NISR data. So back then, we have before August, so there was no NISR data. So we were working on the simulated NISR data. I will show you the actual NISR data, because recently on January 23rd, NASA released a few sample data sets of actual NISR. So I will show you how to work with that in a demo. So these are the simulated data sets and the plots you can generate as a quick, with a 10 lines of code using the tool here. And this is another example from planetary data sets. So these data sets are from Chandrayaan-2 dual frequency SAR, launched by ISRO. This is even currently collecting full polarimetric data over lunar surface. Coming to a quick numbers. So since this framework contains 3 different distributions, sorry for the distorted images there. So the first one is a Python package, which is again distributed in 2 different channels. So one is the Python packaging index, which is called pip, and the other one is called conda. We're kind of distributing the package in the both. So you can actually see, I mean, in the pip, we have like more than 36,000 downloads as of now. And the other one is a QGIS platform, which is a GUI one. So where you can get a UI to interactively process your data. Coming back to the publication, so as I mentioned before, so the technical validation of the work or the usability of the code can only possible in a scientific way is through a scientific peer review, an independent peer review. So we have 2 peer-reviewed journals in journal articles. So first one regarding this QGIS plugin, which we have published in 2021, and it took 5 years to actually publish and put all the things together for this cloud native Python package. So it's got recently published. So coming to the challenges, what we faced during the development at different phases of the development of PolSARtools, there are like twofold. One is scientific and technical, and the second one is community and open source, open science alignment. So the technical one is ensuring the scientific validity. So the scientific validity is kind of a key here, because we used to test each function several times and figuring out bugs. So mostly some of the functions, at least we have some benchmarking softwares which can do that, and for the others we do not have any references to compare our outputs. And even the reference, in the process we even found some bugs in the reference softwares like PolSAR Pro as well. So we reported that and they fixed it later. So this is like a very rigorous scientific validation or technical validation of the output we did. And that's on the other side, it is like computational efficiency. So it is like we need to bring the best of the both worlds. It should be technically correct and also the computationally efficient. So when coming to a CPU versus GPU optimization kind of a framework, as of now, we choose a CPU plus a parallelization. Why? Because a parallelization and also a chunk based, because not every PC is equipped with a GPU as of now, and also because a large chunk of audience mostly do with a CPU. So maybe in future we may go for a GPU optimization, but as of now we have a CPU but optimized with a parallelization and a chunk based processing. So I have to mention here the parallelization and chunk based processing in a context that to give an idea how we process. So a sample nicer scene would be roughly at 20 plus, dual-pol scene will be at 20 plus gigabytes. So if you want to load that into your RAM, so okay, if you have a 32 gigs of RAM, you can load at once. But if you want to process it, you need to at least 22 plus 22 to process and store the output, then for the subsequent steps or so on, at least twice the amount of the RAM, which is kind of, I would expect that most of those domain or non-domain people would have, even in the desktop. And the cloud, we can actually scale it up. You can use a higher RAMs, but here you do not actually need use when you're using PolSARtools, you can actually process that 22 gigs of scene on a 8 gigs of RAM, because we have implemented a smart technique of a chunk-based processing. So we read only a 512 by 512 block, or you can adjust it, and parallelly some 10 blocks and process and dump it to the drive. So we may lose a little bit of the delay when you are directly reading from the hard disk and that, but that is what the trade-off we got for to use it on a low RAM systems and do our parallelization as well. And also cross-platform compatibility we have tested on all the three popular platforms, and we have tested in the cloud native platforms as well. Like as I mentioned before, we have used the multi-mission algorithm analysis platform from NASA, because I was working with JPL and Caltech back then in US. Then I got a chance to use the map platform. So we have tested this framework in the cloud native environment, the efficiencies and how it is handling the technical correctness and so on. So these are the scientific and technical hurdles. And on the other side, we have a community of open science. So open science has a kind of a guideline. So we have we are coming from a radar science, but actually we are going into a software development science, which we do not have any background of. So when we actually submitted our first article to Journal of Open Source Software, so there was a list of requirements so that you are aligning with open source and open source development guidelines. So there is like API level documentations and proper maintaining of the code commenting and everything. So this actually, it's a good learning experience, but it took a lot of time to learn and actually do it. I mean, again, I'm mentioning here, this is all pre-ChatGPT era, but now things are, I would say, may not be that way simple, but at least they made ChatGPT or these LLMs made the way we write code is much more efficient and easy. And also development versus peer reviews, because we are always kind of iterating back and forth the requirements of the community and the reviewers and the development, because we need to catch up with the new sensors and the new techniques and, and so on. And also we have seen people are asking for new features. So whenever we have time, we used to kind of spend and reply back, or otherwise we are kind of open to the peer or pull requests from the community as well. So coming to the key takeaways of this attempt or work is, currently all the space agencies and radars, remote sensing are pushing towards open source, so which is actually transforming and increasing the data democratization and increasing the community. So the data is everywhere now. So now we need the community to use the data. But so the community driven development is essential, because let's say each month there are like tens of new techniques have been developed, and it is kind of very difficult for a small 2-3 people of developers to catch up and implement all those techniques. So we always kind of open to those people who develop new technique to contribute the code so that we can integrate into it. And also the scientific rigor, technical correctness, and also the documentation. So these three are the key, I would say, contributions or key parameters for any open source and open science tool development. So it should be it should be computationally efficient and technically correct, and also it should meet up the demands of the current scientific community. It should also look for what is the more kind of popular techniques or being used in the research articles, so that that's how we prioritize what techniques to use or implement first. Most of them first we implement because from our labs or our network who can directly contribute to the code, and the next priority would be what kind of decomposition techniques or indices have been frequently highly used. So we usually implement that first. So it's the same thing again. The cloud readiness is kind of a must these days because the data is in the cloud. So now the polarimetry actually moved from a kind of a very niche domain to kind of a huge uh, shared resource and a huge community. So which is in a way, when I've also talked with the people who developed the PolSAR Pro, which is like back in 2004, which is like 20 years ago. Back then, the community is way narrow. It is like you can less than 100. So still, they made a huge efforts conducting workshops and publicizing the tool and implementing all those. So we are kind of essentially inspiring, getting an inspiration from those legacy professors or the developers who kind of lay down the way for this open source uh, a tool development, but we are kind of adapting to the new change as well using the same principles. So that's how kind of these are the key takeaways from the development experience what we had. So for the acknowledgements, so these are the kind of developers and the mentors, and also partly supported by NASA-ISRO grant. And also I would like to thank the map platform, because I got a chance to test the tool on the map platform when I was in US. So yeah, we can take a quick look at a demo notebooks available to process whether it is NISAR data or European Space Agency's recently the BIOMASS data, and show them. So let's see a demo. So for those who are wondering where to get this, the recent NASA-ISRO synthetic aperture radar data, so there are 4 to 5 sample data the NASA released recently, like 2 weeks ago. So one data set is over US. So there is over here, which is a full polarimetric data set, and 2 more data sets over here, over this Egypt, and 1 data set over India. So you can go to the Alaska Satellite Facility, or there is other alternative, NASA Earth data. So anywhere. So the key idea is you can actually see the huge size of the data. So each scene is roughly 26 gigabytes. So once you actually downloaded the data, let's say if it's dual polarimetric case, so I can actually, so all the tutorials and the notebooks all are available through the GitHub organization PolSARtools. So we have actually provided clear instructions. It is like one line command to actually install PolSARtools. So it is like, if you are familiar with the Python packaging index, it's just pip install PolSARtools. But if you are doing an automated pipelines in a Conda environment, you can also do this Conda install PolSARtools with a channel name. So once you have actually downloaded the NISAR data, which is actually in HDF5 format, .h5. So with one single line, so this is like import NISAR GSLC, because there are different formats of NISAR. It's like RSLC, GSLC, GCOG. So we have readers for each format. So depending on the format you have, so you can just give the file path and require other parameters, then you can extract it. So as I mentioning the chunk-based processing, here you can actually see we are actually doing a 512 by 512 chunks. It's like 16,000 chunks processing parallelly based on your number of cores in the processor, so that it will be fast. Then it will generate a polarimetric data set, which is kind of a common for, it is kind of independent of any sensor you're using. So you can actually generate a C2 for any dual polarimetric SAR data, but that we need to include in the function, so that from here the rest of the flow is kind of independent of sensor, so that you can use this C2 to kind of use some speckle filtering, so which is usually to suppress the speckle on a SAR image, and you can actually generate some quick looks, so just to see a false color composite of it. Then you can do some polarimetric analysis like degree of polarization or vegetation indices. Similar to the optical, we do have a vegetation indices in radar vegetation indices, dual pol radar vegetation indices, and so on. So with one single line, you can actually generate those, and there is a popular decomposition called entropy and alpha decomposition, and you can also generate this high quality scientific plots. These are like more popularly used in polarimetry, the H alpha decomposition. So you can actually see this is a Shannon entropy here. So here, since these are test data sets, one key observation which we made is something like, so in entropy, you can actually see, and the second image is intensity based entropy, and the third image is actually polarization based entropy. If you see that second image is much more cleaner compared to this banding and the polarization based entropy, which means still the NISAR data is in actually calibration, so they have calibration issues in polarization, so which you can actually, if you do a polarimetric analysis, you can actually see that on images. So coming to the full polarimetric scene, this is over US. So we have a similar structure. You just import the GSLC scene, and once you got a C3, so if for full pole it will be a C3 or C4. For dual pole it will be a C2, we call the polarimetric matrices. Then the rest of the flow is again sensor independent, and you can generate a same quick look. But here you can generate a 3 parameters since you have more channels. So a 3D plot also you can plot. Again, you can do decompositions and different types of plots. As I was mentioning, we have also recently included European Space Agency's BIOMASS mission data. So BIOMASS recently released, I think, 2 weeks ago after NISA, like 1 week ago. So since we have had this reader to extract those polarimetric data, so again, this is a scene over India, Indian east coast of India. So again, this is again another data format. This is a we call GRD or intensity based data format. This is not a polarimetric data set, but still you can actually do a kind of pseudo polarimetric analysis using these data sets and the tool. So compared to the, apart from this processing, as I also mentioned, that this tool is also kind of, you can use it as for the educational tool, for the teaching and other things. So these are kind of what we call polarimetric signatures and polarimetry. So what it shows is for any given ideal target, so how based on the wave orientation and electricity, how the signature, how the intensity varies, the power from that particular target. So this is kind of an ideal one. And if you want to see, you can actually represent it in different ways. Like you have a Poincare square representation, and you can actually see those ideal theoretical plots just to teach those concepts of like what is a Poincare sphere, how you actually represent a polarimetric data over this, and how an ideal target looks like versus how an actual target looks like. It will be distorted. So this is kind of a this comes into the calibration procedure of the SAR data. So it is something like both research oriented, teaching oriented. So the documentation is there. So it's a well structured documentation with any function you can click on, and along with the notebooks, so you will find entire details of all the parameters and use case. So with that, I would like to kind of conclude this talk. So yes, thanks for your attention. So if you have any questions, so you can take, we have like more than 15 minutes.
Awesome. Thank you so much. Yes, we've got plenty of time for questions. If anybody in the audience has any questions, go ahead and raise your hand and I will call on you to unmute yourself. I think I can go ahead and maybe kick things off here. First of all, thank you
Yep.
for showing the demo. I completely agree with the making sure that documentation is readable, making sure that it kind of complements the tool. It's something that I work on very heavily over at the Goddard Earth Sciences Data Center with our Jupyter Notebook tutorials. Um, and I actually was really intrigued by your slide about some of the challenges with that. Um, Certainly, casting as wide of a net as possible, but knowing for the tools to support in terms of Windows versus Linux, but knowing the user base is also critical as well. And I was wondering, do you find that because you're working with level two data, level one data, even that sort of impacts your user base or has led to maybe a different level of, I guess, experience required for getting started with Pulsar tools?
Yeah, it's a good question. So yes, usually we do in specific to polarimetry, we can mostly in a classical or traditional way is we only go with the level one data, mostly the SLCs, whether it is RSLC or GSLC, because in a level two data we don't have the phase of the signal for any pixel, so we call it as it's just an amplitude data. So still, I mean, even I've also contributed to that amplitude-based polarimetry. It's kind of pseudo polarimetry we call. That's why. So most of this stress, because it's a in a way that we have made a decision or kind of a prioritized mostly the level one data, because we can actually do much more and data rich and has a actual scientific kind of base. Not neglecting the level two, because and also for the level two people, I would say it is similar to an image processing one. Since it's an amplitude, people can easily deal with that even with a QGIS or any popular image processing softwares as well. But the complex numbers, let's say I will give you an example of Google Earth Engine, which actually revolutionized all this cloud-based Earth data processing. So where the challenge is dealing with the complex data. Still, even Earth Engine couldn't figure out, because yes, you cannot kind of resample the same way you do with the amplitude with the phase. So that's the one bottleneck. So that's why since there are enough tools, if they want to deal with the level two, availability is there, so that our priority is less, not neglecting, but we have limited tools on that. But mostly our focus is on that level one, so that people will get not scared away by this complex processing of polarimetry, because by hearing the term polarimetry, people are getting scared away. I've seen that's why we have a very narrow limited community now. So the motivation is just give people a few lines of code, so that at least they will see by themselves the results. Then they will start learning where it's coming from, rather than writing their own code, which is kind of a nightmare for most of the people. So
Yeah,
yeah.
and also you've already got different things like Conda environments available, which are huge. It makes it so much easier to set up. Um, I guess from that kind of standpoint, um, what are some other takeaways that you've had from demoing Pulsar tools, just kind of like in a real world scenario? Do you find that it performs well when you're running in the cloud, so in AWS or with Google Colab, or
So in Colab or AWS, I would say I haven't seen any kind of performance differences, whether it is a desktop environment or cloud environment. So as of now, it is mostly like it's the difference comes from when you have a faster SSD, because EC2 will have those faster throughput of it. So there, obviously, you will get much faster outputs. I mean, in the performance, but it's not the algorithm issue. It's actually the hardware dependence on the hardware. So if you have like a faster SSDs, definitely you will get faster one. But if you have a normal hard disk, which is like a traditional one, because this is corely dependent on the chunk-based processing. So you're not actually loading the entire data once. So that delay or latency is always there as a bottleneck, just because you want to support a wide variety of systems. Again, if someone seriously have huge RAM, then they can actually adjust the block size to kind of a huge unrealistic number, so that entire data will be dumped there into the RAM and processed. There is an option. So, but default options are this. So yeah.
Yeah, that's one of the reasons that I'm really happy that they chose HDF5 for all that sort of stuff. Just being
Yeah.
the cloud optimized format.
Yes, cloud optimized HDF5. That's the first ever, and even they are kind of introduced a new driver, not yet public. I think the GDAL driver. Mostly we are relied on GDAL. So this cloud optimized HDF5, it doesn't have a reader before this. So JPL actually, personally, this Marco Level. Marco Level is actually pushing that so hard to make that driver, so that people now can directly drag and drop those HDF5 into QGIS. That's what the kind of,
Yeah,
but still QGIS still doesn't support a complex data type. So they can do with that amplitude data level 2, but level 1 is kind of, we don't know when it will support, at least 2. So one smart technique European Space Agency did is they are actually separating those amplitude, the I versus the, what do you call, AB, the intensity versus phase, into two different channels or two different bands of a geotiff, so that you can load into it a QGIS. Though it may not look good, but at least you can load and visualize which part of the world it is and how the data looks like. But yeah, you have to see. It's a kind of, what do you call, decisions made by those high level decisions they made, the science teams.
yeah, that'd be incredibly useful. I love QGIS. I used it throughout my
Yes.
research. Yeah, so that'd be a fantastic tool. Um, I guess kind of going along those lines, are there any other developments coming up with PolSARtools with any new releases that you'd be able to?
Yes. Currently, we are updating even nicer reader. Like, since in SAR we have like sigma naught, gamma naught, beta naught. I think I missed that by default. Nicer is giving a gamma naught or something, so I have to include that, and also incidence angle. I have to deal with that too. So kind of there are works. Recently, I moved, like in October. I moved to India. So since it's in my new job and I'm kind of getting settled in and getting used to it, and I not able to get time, I'm not able to get time to spend it on as a developing, but still we are doing, other people are there, we are adding new functionalities. And even just 2 weeks ago, the BIOMASS, the ESA team released BIOMASS. So right in one day, I sat for it, because people want to take a look at the data. I mean, whenever the data announcement is there, so obviously people are curious to whether they need to use it for the scientific analysis or not, but they want to see first look. So I wrote that biomass reader, kept it. So again, these are like first kind of codes. Again, we have to do next versions of it. So currently, I'm thinking of including other ISRO, the Indian satellites as well. But again, it's a time factor. So
Awesome. Yeah, that's a lot of
yeah,
great. Yeah, and
it's always keeping up to the community demands. Whatever makes the news headlines, follow up the flow. So
yep, absolutely.
yeah.
Do we have any other questions from any other attendees? Okay. Well, thank you so much for joining us. I
Yeah,
think
thank
in
you.
the time that I've worked with this committee, I believe you are the farthest international from where I'm currently sitting to
Oh,
the webinar. So thank you so much for joining us.
yeah.
And I hope you have a great rest of your evening. And I look
Yeah.
forward to keeping in touch.